We have seen that to build a scalable quantum computer, we need to build a complex electronic interface operating at cryogenic temperature as close as possible to the quantum processor. To do that, we need to meet a number of challenges in terms of performance, power dissipation, and of course we must find electronics that can work at cryo temperatures. Let's look now to some of these issues in more details. Let's start from the cryogenic operation of the electronics. So, which is the best electronic technology that can operate at 4 Kelvin, at 20 millikelvin, or even below? There are different options. First, we can think to use superconducting devices like RFSQ, RQL, and so on. These devices operate naturally at very cold temperature because they exploit superconductivity. And one additional advantage is that they have very low power dissipation. Next to that, another option is to take standard semiconductor technologies and look at what is the minimum temperature at which they can operate. One problem is that some of them, like the first line here in this table, cannot operate at the temperature we need because this device doesn't work below 100 Kelvin. Other technology really works at 4 Kelvin or even below. For example, these two types of devices, silicon germanium HBTs or MESFETs, are very much used today, also for quantum application, because they operate at 4 Kelvin or below and can operate with very low power dissipation. However, if we really look closely to all the technologies, there is only one of the technology here that is very special. That's the last one shown here, the CMOS technology. CMOS stands for complementary metal oxide semiconductor, and it's the same technology that is used to implement conventional microprocessors. It is the only technology in this list which can offer very large-scale integration, which basically means that we can integrate billions of devices on a single silicon chip. But why is this relevant here? Because we want to build a very large-scale quantum computer with millions of qubits, and of course, also the electronic interface would be very complex. And CMOS is the only technology today that can offer such complexity, comparable to what is done in conventional microprocessors. So we want to use CMOS, because it also works at 4 Kelvin and is proven to work at least down to 30 millikelvin. In fact, we don't know yet what the minimum temperature is at which the CMOS can still operate. So, if you want to build a scalable quantum computer, the best approach, and that is what researchers are doing today, also here at QTech, is to research cryogenic CMOS technology, or cryo-CMOS in short. So we want to build all this system here using cryo-CMOS. But before we can do that, we have to look at two specific problems. First of all, which are the exact specifications that this system must satisfy? And second, how exactly do cryo-CMOS devices operate at such low temperatures? Let's look at the specification first. Specifications are very important. Since we have to build a tailor-made system, we have to be aware what the impacts are of any choice in the electronics on the qubit performance. What researchers typically do is to simulate cryo-CMOS electronics and qubits together. The main idea is to start from a circuit simulator where you can simulate the electronics. This simulator produces the electrical signals that can be fed to a qubit simulator, which is basically a full physics simulator using the Hamiltonian description of the qubits. From operating the qubits in this way, you can derive what the fidelity of the full quantum computer is, at least for the control part. Next, the qubit simulator can also produce the electrical signals generated by the qubits, and this can be fed to the circuit simulator to emulate or simulate the readout process and finally get the fidelity for the readout too. By doing this, the designer can really adapt the electrical circuits for the best performance of the full quantum computer. In order to be a little bit more pragmatic, let's look to an example. So we know that in order to operate a single qubit rotation, you need to produce microwave pulses. This can be done as shown here, for example. You have an arbitrary waveform generator, which produces a certain waveform, For example, this square pulse shown here in green, that is multiplied by sinusoidal carrier coming from the oscillator shown in blue. So the result of the multiplication is a short pulse at very high frequency. This is what you can fit to the qubits to do a single qubit rotation. Now, the question is, how precise should this pulse be? With the approach I've shown you before using the simulators, we can analyze any error or non-ideality in this pulse and find out how this relates to the final error in the full quantum computer. In this table, we show all the possible sources of errors in such pulse, such as amplitude errors, frequency errors, noise in the amplitude, noise in the phase, and so on and so forth. And we can compute, here at the bottom, the 1000 part per million total error that a pulse, assuming all these error sources, will produce in the quantum computer. This error would result into a 99.9% fidelity for the qubit operation. In this way, we can really relate qubits and electronics and find out how good our electronics should be. The follow-up question is it possible to realize a circuit with such specification or not? To give a first response, let's look at what we can do using CMOS technology, but at room temperature, not cryogenic. Here, I took as an example a practical implementation for the green block and the blue block. So we can use a digital to analog converter to implement the green block and the so-called phase locked loop for the oscillator in blue. By choosing specific parts, we can see that such a system would consume a total power of 37 milliwatts for a single qubit. So, first of all, we can conclude, yes, it is possible to make such electronics, but we consume quite some power. We can imagine that if we have to replicate this for thousands or millions of qubits, it's going to dissipate a lot of power. If we have to operate such circuit at cryogenic temperatures, we have a problem because it's not easy to dissipate a lot of power at very low temperatures. But we can be a little bit smarter, and we can do this. We can make sure that this circuit is not only addressing a single qubit, but a number of them. For example, by multiplexing them in frequency. By doing that, we can, for example, address up to 64 qubits with the same circuit. Of course, this would require some modification in our circuit. So you see that the number at the bottom changes. As a final result, we have higher total power, but we are addressing more qubits, 64 in this example. So we can get less than 1 milliwatt per qubit. So what is the main idea here? The challenge is that when we design the electronic interface, we have to look at the system level. We have to co-design the qubit processor and the electronics in order to make smart choices that makes all of the electronics possible, for example, in terms of power consumption. But up to now, we have seen examples only based on electronics that works at room temperature. Let's look to how those devices would work if you go to cryogenic temperature. Here, I want to show you how a single CMOS transistor works. Basically, a CMOS transistor is nothing else than a device that regulates the current flowing through two of its terminals, the so-called IDS, as a function of the voltage that you apply on the other terminal of the device. Here on the left, you see the current generated by a CMOS transistor at room temperature as a function of the voltage applied to the current terminals. Ideally, you would like that this current is as flat as possible and independent from the voltage at the ends of the transistor. In this plot, you see an NMOS and a PMOS, the two devices that are present in a CMOS technology. In fact, the C in CMOS stands for complementary technology, meaning that you have two different kinds of devices. But that's not very important for the sake of the following discussion. What is more interesting to see is that if you cool down the device, what you see is that the current increases. And that is good, because more current means that the full circuit can go faster. So you have an improvement in performance. But this is just the cooling only down to 20 Kelvin. If you really go to 4 Kelvin, what you can start seeing is a very weird behavior, because you see that the current is not anymore flat, there is a strange effect. And you may also see that there is some hysteresis in the current. So the current is different if you sweep the voltage in one direction or the other. And that's very different behavior than what we see at room temperature. Are we able to handle that? In order to understand this phenomenon a bit better, we can look at how different transistors in different CMOS technologies behave at 4 Kelvin. In our measurements at 4 Kelvin, on the left, you can see exactly the behavior we have just discussed. The current is not flat, as it happened at room temperature, but it shows this funny kink. On the right, instead, there is a different CMOS technology, and here you can see that the curves at 4 Kelvin really behave similar to what you would expect for a transistor at room temperature. So you have these very funny different behaviors. But the nice thing is that we can predict such behaviors. I can take the standard model used for those devices at room temperature and extend it to cryogenic temperature. I can show here that this model, shown as the solid lines, fits very well the measurement data, shown as dots. What is the bottom line here? Basically, by using the standard models and the standard techniques, I can model these devices also at cryogenic temperature, so that I can really use them to make electronics that work at cryogenic temperatures. So by using the techniques, I will be able to build such complex systems. Here at QTech, we have already started implementing a number of blocks that will be the basis for building such a large system. For example, we have investigated how to use standard digital circuits like FPGAs operating at 4 Kelvin and below, and how to build temperature sensor integrated on silicon, RF oscillators, and low noise amplifiers, all operating at cryogenic temperature. All these blocks are required into the electronic controller for quantum processors. And this cryogenic electronic interface will enable us to build the scalable quantum computers of the future.